So what is ARA injection? Hi everyone, steel is everywhere from building to railways and most of it is made in blast furnace which unfortunately also emit a lot of CO2. In this video we explore a powerful tool to reduce those emissions. So it is auxiliary reducing agent. So what is ARA? These are the material like hydrogen pulverized coal, torrefied biomass or waste gases injected through the tuyeres to partially replace coke. In this Venn diagram, we have a big picture. Blue, which signify ARA reduces coke use and CO2. Orange signify that it need precise control of work well, and green, it tells a whole story about our major step towards net zero steel making. Now, coming to our subsequent next slide, where we can see that how ARA efficiency can be dependent on coke replacement ratio or RR. This tells us how many kilogram of coke are saved per kilogram of ARA injected. And here a formula is shown. RR is equal to delta K by S, where delta K is coke saved and S is a ARA injected per ton of hot metal. So here RR1, RR2, RR3 is given. RR1 comprising is basically comprises of two stages. One is the baseline stage when we don't have injectant, and uh, the second case is of with a injection. So it is basically deriving is comparing before and after coke rates. RR2 similarly comparing to different injection rates. RR3 is about a differential approach for especially utilizing modeling. But RR is not constant. It depends on type of ARA, like it's a hydrogen, coal, or natural gas. It also have a dependency on ash and moisture content. It also has a more dependency on gas temperature and raceway condition. So we can say that high RR is good, but efficiency can drop if you over inject without proper control. So we need a smart way to inject in order to have a maximum result. So managing injection efficiency, what is that a smart way? So here we want to show you that efficiency can drop because of many reasons, and few of them are: the raceway gets cooler with a hydrogen rich ARA, gas flow may become uneven, some ARA do not fully react in time. So this is where blast furnace science matter. The raceway is a fast reacting high temperature zone, and if ARA doesn't convert fully there, it create shoot or unburned residue. So now question arises, what can we do? So all knows that inject oxygen to maintain heat or flame, preheat or dry the blast to raise the flame or RAFT or Raceway Adiabatic Flame Temperature we can say, and adjust the injection rate carefully. So we can say that efficient injection is not about injecting more. It is about injecting smartly, as we have already come across the slide content and come to this conclusion authentically. Now, what makes a good ARA? Different ARA behave differently. As we know, coal vary from anthracite to lignite. The best one for injection is those having a higher fixed carbon, medium VM, and low sulfur and ash. So these are the primarily lifeline. Now coming to the biomass is also eco-friendly, and it but comes with downsides. Now, high moisture, low density, poor grindability, all these uh, often leads to a appeal towards blending biomass with coal to get the best both of both like a cleaner emissions and a stable combustion. So we have to choose uh, the purposes, and we have to match our agenda of sustainability in using this biomass. Now coming to the raceway chemistry and cool behavior, as you must be knowing, in the raceway reaction time is just millisecond, and that's where coal reactivity matters. High volatile coals convert faster but doesn't provide enough heat. Similarly, low volatile coals burn slower but supply more energy. So now we have to blend both of them to derive our best results. Petrography also plays a very important role, like vitrinite and liftinite. Uh, High reactivity is ideal for injection, as we know. Inertite, where inertite question arises, it matter for a high carbon but sluggish reactions. So we can even add carbonate or nitrides to act as a combustion booster. So while deriving the best efficiency, knowledge of these petrographic aspects is also needed tremendously. Now, coming to the co-injection strategies, we can say that for combustion to be effective, ARA must meet oxygen right at the tuyere. Advanced lance design like coaxial, eccentric, turbulence enhancing lances, it all helps improving mixing and particle dispersion, and this all leads to enhance combustion, prevent dead zone, and improve raceway flame stability. So we can say that this proper launch geometry is a basically hidden hero in efficient ARA injection. Co-injection strategy, another powerful tool, combining coal with a natural gas, our oil balances out. So all these work well. So we have to see that the temperature control, the gas chemistry, reactivity, all should align. Thus, by adjusting the blend ratio, we can fine tune the furnace thermal and chemical profile, and a core equation helps calculate how much oxygen is needed to match different fuels and maintain stable combustion. All these can navigate us towards better burnout and efficient results. Now, dealing with the RAFT drop, we can say that hydrogen rich ARA reduce iron ore efficiently, but they absorb heat also and reduce flame tremendously due to their endothermic nature. To fix that, uh, we enrich the blast with oxygen, as we know, increase the blast temperature or reduce blast humidity. But we must be careful in oxygen regulation, because all the time oxygen remains very costly affair, and we have to evaluate in cost benefit analysis very smartly. Also, we have to see that too much oxygen users can overheat the Tuyere zone and create a aggressive situation where many times adverse effects may be expected. So hitting the right operating window to keep the furnace running efficiently at right ARA rates, we calculate required flame, top gas temperature, gas permeability. These all tells how much ARA need to be injected without destabilizing the process. So it's a balancing act between chemistry, temperature, furnace geometry. This is where CFD modeling or AI based control or deep understanding of materials comes into